Okay, so finally I want to talk about the discrete Fourier transform. Finally, at least for this part of it, of the lectures. So, the discrete Fourier transform is this implementation here, the sum from n equals 0 to n minus 1 Cn e to the minus 2 pi I mn over n. Okay, so it's a mapping. It takes a vector Cn and it gives you a vector Cm hat. Okay, it takes a sequence of points and it maps them from one to the other. And the inverse Fourier transform discrete Fourier transform is almost identical. I should do it the opposite way here. So we go back. So the combined together, you end up back where you started. The sum from m equals 0 to n minus 1 Cm hat e to the power, and it's the same 2 pi I mn over n. Okay, it's just a positive instead of a negative here. It conjugates, just like inverse Fourier transform, and it has this 1 divided by n. Okay, so it scales differently. And this is slightly important, and it loses some of the symmetry by having that, but if you had 1 over square root of n, I guess that would just cause confusion to people. Okay, and we've already seen how we can connect the values of Km with the values of, and you saw that expression in the previous derivation, how to get the expression for K, how to get the expressions for Km, where they come from. So implementing this thing here naively, you'd end up with doing, it's just a matrix multiplication, so it's an n squared operations to go, but they can be massively sped up. So discrete Fourier transform is order n squared, and the fast Fourier transform is order n log n. Okay, so that's an enormous speed up, because of course if n is the 1000, so this is equal to 1000 10 to the 3 squared, and this is equal to 10 to the 3 times the log of 10 to the 3, which is approximately 3. Okay, so every exponent. So increasing the factor of points by 10 here barely makes any change, and just increases this one increases the, it's going to make it go 100 times slower. This is going to make it only go 10 times slower. So it's an incredible speed up. It's proved to be an amazingly useful algorithm, and of course the Fourier transform was something very natural. Okay, it's not in the notes, but how the FFT works is really simple. So the idea behind the FFT is it's an incredibly simple idea. And it actually has appeared in lots of guises. Apparently Gauss knew about it, but it was published. I can't remember the guys' names actually that came up with it. Okay, so here's how it works, right? So you've got this expression Cm hat is the sum from n equals 0 to n minus 1 of Cn times e to the minus 2 pi I mn over n. Alright, so one of the things about the fast Fourier transform is that it's only quicker if the number of points is a power of 2 or something that you can factorize. So the more prime factors it has, the better, and if it's a power of 2, it's optimal. And if it's a prime number, if n is a prime number, then the system doesn't work at all. Okay, because what we're doing is we're going round, we've got a sequence of points on the circle that we're computing, right? And so the first time we go round, we take every point. The second time we square it, so we take every second point. And then we sort of coming back on ourselves, essentially, is the idea. Let's just do it in maths. Okay? So we assume that n is even. So we can write this as the sum from n equals 0. N equals 0 to all the even numbers, 4 to n minus 2, of Cn e to the minus 2 pi I mn over n, and the sum over n equals the odd numbers, 1, 2, 3, 5 to n minus 1. Cn doesn't seem like I've got anywhere here, does it? And then we can look at each of these in turn. So this is just another Fourier transform on half the number of points. So it's the sum from k equals 0 to n over 2 minus 1, c of 2k e to the minus 2 pi I k times m over n over 2. Right? So it's a Fourier transform on half the length. And this is more or less the same. We've got to pull a factor out, which is just a constant factor, 2 pi I mn over n over 2. And then this is the sum from k equals 0 to n over 2 minus 1, c of 2k plus 1. So it's every second point here, but it's still just another Fourier transform. Alright, so we can basically write this. So this is a Fourier these are just two Fourier transforms of half the length. So if you think about it like this, so let's assume n is equal to 1,000, 10,000, right? 10 to the 3. So this thing here, we're going to have to do this one Fourier transform here. So that's going to take us the n squared, right? So n squared is 10 to the 6 steps. Now if we go down here, we're going to do it half the length. So it's 500 squared plus 500 squared. Okay, so this thing here is going to take us 10 to the power of 6, and whatever is 500 squared. So right, so this is like a quarter of 10 to the power of 6 plus a quarter of 10 to the 6. So it's a half 10 to the 6. So by just by factorising and breaking it into two FFTs, we've halved the amount of steps we have to take. And then we can just keep applying that sort of remorselessly. And if n is equal to not 1,000, but if n is equal to 1,024, then we can just keep it halving forever. Okay, so that's the idea. It's not rocket science or genius. I mean, implementing it efficiently and things might be clever, but there's nothing very sophisticated about the idea. And you can sort of see what's happening as you go around the circle. On every even one, you only land on the even numbers, so you only need every second number. And every odd one, you kind of do the same thing.